And most all of you, in fact, I believe I can say this truly, all of you have been in a physics class. So between biology, chemistry, and physics, can one of you define energy? Jake? How many of you understand that statement, the ability to do work? Okay, it's a good statement, and I would agree with you that when I was a younger teacher and I was just starting out, I used to love definitions like that because they incorporated so many vocabulary words. Unfortunately, as I've gotten older, that definition tends to have certain problems and limitations. Because when I ask a student to explain what that means, I usually get a pretty large variety of responses. In fact, that's what I'd want you to do now, because I was hoping that would be what somebody would say, because that's exactly what I taught last year. So at your table right now, explain what that sentence means, the ability to do work. I'll wait 3 minutes, and then I'm going to pick table by table for you to tell me what it means. Okay? This statement, and take a look at this. I have a configuration of charges. So just a random group. I don't know what they are or what their values are, but they're just a random group of charges in space. From our discussion last week, we already know that there must be a certain amount of energy associated with this. If for no other reason, to go back to your idea about energy, is come up with a way of describing the changes in energy due to these kinds of systems. But we don't really know what happens. We're just kind of making it up. So when we look at like this picture, if I wanted to take these charges and just move them around, like take Q4 and move it over here, so Q4 is here now, and move Q3 right here, so it's right over there, and take Q2 and put it way over here to Q2, and then take Q1 and maybe move it out a little ways, so it's right there, and I'll leave Q5 where it is. And this is going to be my new arrangement of charges. That is going to take energy, because this new configuration, this new change in all their positions, changed how much energy had to be there. Their proximity changed how much force was required to move them. It took force to move them from one place to another. We know work had to be done. So we now have a new energy state, which I'll call U final. And ultimately, just moving the charges around required a change in energy, which is the strict definition of taking the energy that was there before and comparing it to the energy that's there now. Now, this part is important. Physicists have grappled with this to try and find a uniform and consistent way of dealing with the kind of work done with conservative forces. And they have decided that this will equal minus the work done against a field. This is a solid and not changing definition. We are, as a human species, defining the change in potential energy as minus the work done by the field. Now, you might have concerns about all of this, but this definition, this delta U equals minus W, needs to be memorized and indelible in your brain. The negative sign. And I'll explain why. There is a clear natural precedent for why this is going to be the de facto standard. And I've already talked about it, but not in a way that brought math involved. The first particle. How much work does it take to put the first particle here? Zero. So, someplace far away, I give a particle that also has charge, kinetic energy. It has real, tangible energy equal to 1/2 mv squared. That particle eventually makes it to a spot right here where it stops. So at this instant, the velocity is 0. Now, we know by definition that anytime an object's kinetic energy changes, work had to be done to the particle. We call that the work energy theorem. And it simply states that work equals the change in kinetic energy. Now, you guys should remember that from your first run through physics, but if you don't, remember it's a motion equation. Do you guys see what I mean when I say a motion equation here? This is 2a delta x equals v squared minus v naught squared. That's the motion equation that says work equals a change in kinetic energy. A little manipulation and I get ma delta x equals 1/2 mv squared minus 1/2 mv naught squared. Right? Force times displacement. Final kinetic energy minus initial kinetic energy. The work energy theorem. We good with that? Now, the statement I just made about the change in energy of a system is cooperative with the work energy theorem. In this instant, the final kinetic energy was 0. And the initial kinetic energy was some value related to the velocity. By definition, the work done had to be negative because the final kinetic energy was 0. Right? By definition, we know that this particle was stopped by the electrostatic force. So it could be shown that the work had to be negative to stop the particle. Now, this isn't a surprise. In gravity, we do the same thing. You fire a rock upwards, it eventually comes to rest. We state that that energy didn't go away. We state that that energy got transformed from kinetic energy into potential energy. That's exactly the statement we're making here. When we say that delta U equals minus the work done by the field, we're also making a statement that this leads to changes in kinetic energy. This statement is the statement that tells us that you can take the kinetic energy of an object and store it as potential energy, and that the conduit for doing so is the conservative force between two particles. Now, like it or not, this statement is a guiding principle about the positivity or negativity of work and energy. It's going to get more complicated than this, so let's deal with this example for a little bit, okay? Just a few examples from here to get an understanding of how we're going to deal with energy. Because in a few minutes, we're going to have to ramp the math up. So let me look at a case we've already looked at, but from the standpoint of a field. So I have a uniform electric field. I put a particle there. The particle will not naturally move from this location to this location. It won't go there on its own. Do you understand why? If it's a positive particle, the field can't make it go that direction. However, it is possible to describe the work done by the field, even though the field can't be the thing that moves the particle. Now, I understand this argument I'm about to make is got to be the most ridiculous argument there is. But you have to be able to hear the problem stated this way, because they'll talk about this in an FRQ. So right now, we know that there is a force on the particle in this direction, and the size of that force is equal to Q times E. So for this particle to move a distance d through this field, the work done would have to be equal to the integral of f dot dx. We talked about that last week. Well, dx is going to be to the right, but the force from the field is to the left. So the work done is going to be QE times dx times the cosine of the angle between x and E. And I have to integrate that from 0 to D. I'm going to keep going. Are we okay with all of that? So that means Q and E are a constant. Pull them outside the integral. Integral of dx from 0 to D times the cosine. Now I have to deal with this angle. The angle is 180 degrees between the force and dx. Right here, that's 180 degrees. So that gives me a cosine 180 degrees, or pi. This means by definition the work is minus QE D minus 0, or minus QED. The amount of work done by the field when the particle is moved from one side of this field to the other. So you're asking, well, why does the field do negative work? It's because of the way we defined negativity and positivity. Our particle now has a change in potential energy equal to minus the work done by the field, which must be minus negative QED. Meaning the energy is stored as electric potential energy in the amount QED, which is positive. There's a positive amount of energy. Now, you've got to be wondering why I'm making such a big deal about this and why I'm harping on it so much. And that we can have a negative charge, a charge that behaves in the opposite manner of your field. And therefore, dealing with energy and direction becomes more complicated because we know that the electric potential is going to be related to the potential energy. And the potential energy doesn't have direction, but involves the positivity or negativity of our charge. So the biggest statement I need you to make is that if you do work against a field, the particle is going to gain potential energy. By definition, the work being negative by the field is a consequence of the fact that if the particle came into this region with kinetic energy, the field would take that energy and convert it into something else. Understanding whether it's going to increase the kinetic energy or decrease the kinetic energy is the real statement about the nature of positive or negative work. Negative work takes away kinetic energy. Positive work gives something kinetic energy. So you guys would have had no trouble with this discussion at all if I had started by placing the particle on the other side. So if I have my field again here, and I'd place the particle here and asked, well, how much work is done by the field when it moves to here? Not one of you had had an issue with it, because the force is in this direction on the particle, dx will be in this direction, the field will push the particle, so by the time the particle gets here, has it gotten more energy or less energy? It's hard to think it through all the way, but this particle, in going from this side to this side, is probably going to make it to the other side moving pretty quick. Right? I just let it go, and by the time it makes it to the other side, it's probably flying. But the truth is, it lost potential energy. It had to lose potential energy because it gained kinetic energy. So its travel from here to the other side had to change its kinetic energy, increase its kinetic energy, which meant it had to lose potential energy. So the work was positive in going this direction, but delta U was negative. The change in potential energy had to be negative from the right side to the left side. That resulted in the particle having kinetic energy over here. I'm getting to it, and I know I need to get there faster, but if this is the ground and here's a house, and I have a rock, and I lift the rock up to here, a height h, how much potential energy will the rock have? mgh. No one has a problem with gravitational potential energy. But to lift the object, I would have to apply a force. If we're talking about the force from gravity, what direction is the force from gravity? So there's a force downwards, mg. If I want to lift it, or if I want to talk about the work done in moving it, h, the direction it would have to move is upwards. So the work done would have had to be the integral of mg times dx times the cosine of 180 degrees. Right, lifting the rock does negative work by the field, which meant a change in gravitational potential energy that was positive. This never really mattered when we talked about the rock, because there was no chance of having a negative rock. All the rocks were positive. The reason why we have to be so specific is I placed the first charge there, Q1, and I want to bring Q2 right here. I could have fired Q2 from a cannon far, far away with enough velocity to make it up to this spot and just come to rest. Now, it might not stay there, but for that instant, its kinetic energy was enough to get to this point. Does that make sense? Now, if it comes to rest, that kinetic energy had to go someplace. We know ultimately that it had to do with the interaction between Q1 and Q2 that brought Q2 to rest at this point. But what we don't know is necessarily what happened to that velocity. We know that a force was applied to charge 2. We know that that force caused it to slow down to a stop, but it wasn't like something was taken away from Q2. We know that if there was nothing physically to hold it in place, Q2 would probably not stay there, right? It would repel and go back to where it came from. So we know that that energy got taken up and stored between these two particles. What we're trying to grapple with is look, I don't know where it went. I really can't figure out what happened to that energy. There was something very clear about the particle that was measurable initially, the velocity, something that is viewable to any reference frame. The idea that the particle was moving. And now it's not moving, yet the quantity that would have described this particle's motion is still somehow stored between these two. Which is why potential energy requires this concept of an interaction. That somehow there's something happening between these two particles that can't easily be described. That stores energy. That somehow takes this kinetic energy that was visible, measurable, and easy to see, and invisibly places it somewhere else. And it might as well be magic. That's why we use words like capacity and ability, and even the word interaction, to somehow describe where this kinetic energy went, where the velocity went. And we just use words like conservative, that there was a conservative force. A conservative forces conserve energy. Sure, all of that's true, but we have no idea where the energy actually went. What we do instead